Hi, welcome to my channel, JaberTime. Today I'm going to go over change of variables in multiple integrals and the Jacobian. Change of variables in multiple integrals, which is in general called the Jacobian. Okay, let's go back and start again. Hi, welcome to my channel, JaberTime. Today I'm going to go over change of variables in multiple integrals, and in general it's called the Jacobian, or the main part of it is called the Jacobian. Let's get started. So what we have is, as an introduction, in one-dimensional calculus using substitution, we could change the integration from a to b of f of x dx to different letters in terms of u, and of course the limits changes from c to d. We know this, and we have to be careful with the u substitution. A change of variables can also be useful in double integrals. One of the main ones that we use all the time is x equals r cosine theta and y equals r sine theta, which is called polar coordinates. So when we go from x and y system to r and theta system, we have the region R that gets mapped to the region S. Any point that is going xy will be imaged to r theta. So the double integral over the region R of f of xy dA, where a represents the limitations of r, will be transformed to double integral over the region S of f of r cosine theta, r sine theta, r dr d theta. So dA changes to r dr d theta. One of the main things about the polar form is it's useful in a lot of different sections and applications, especially when you have circles. That's the best way to transform your function and its limits to polar coordinates system. In general, we consider a change of variables that is given by a transformation t from the uv plane. So it doesn't have to be called usually x and y to start with, to the xy plane. This is in general. I'll show you some more and some examples. So the transformation will take you from uv to xy. That's in general, from uv to x and y plane. T transforms S into R. X is a function g of u and v. Y is also a function of the same u and v. Or in short, we could say x is a x of u and v, and y is y of u and v. Let's take a practical example to see how the transformation changes from this shape to a completely different shape. A transformation is defined by the following equations. X equals u squared minus v squared. Y equals 2uv. Find the image of the square. That's the easiest way to start with. The original S region is uv such that u ranges from 0 to 1 and v goes from 0 to 1 also. Let's keep this in mind. Okay, this is the way we transform from xy, or sorry, from uv to xy. So here's the square that is described on the axis u and v from 0 to 1, from 0 to 1, and v from 0 to 1, and it's a square, so that's how it looks like. Now, of course, we can't transform every single point, but what we do is we transform the sides and everything will follow. So we focus on the sides and the corner points and so on. Looking at S1, down below right here, we know a few things. As I said, keep this in mind. And we're walking on this line segment, but that says that V is 0. So if V is 0, I could just plug in V equals 0 here and plug in V equals 0 here, and I end up with the following: x equals u squared minus 0, which is x equals u squared, y equals 2 times u times 0, which is y equals 0. So it's not too hard. It's just like a new way of solving and changing the language, let's say, transforming units and letters to a different units and letters. So now we know that x simplifies to u squared in the xy plane and y equals 0. But what happens to the u? U changes from 0 to 1. U changes from 0 to 1. Well, if u changes from 0 to 1, x will change from 0 to 1, because x is written as u squared. X depends on u, but u changes from 0 to 1, so x changes from 0 to 1. Y is 0. The way it changes from 0 to 1 following u squared, meaning it changes the speed as you go, but still it's a line segment, as you could see. This is x and this is y. Y is 0 and x takes values from 0 to 1 because u goes from 0 to 1. That's the first segment. It's not always looks like the same, so let's take care of S2. I know I'm slowing down, but I need to speed up later on so you could get at least the idea. It's like a puzzle. You work back and forth and transform everything with the limits that you have. Let's look at S2. Well, S2, right here, we have some limitations. U is fixed to be 1. It's right there. And V changes from 0 to 1. I keep that in mind. Well, if U is 1, I could plug it in here and simplify this to 1 minus V squared, as you could see. 2 times 1 times V, which is 2V. Now, use substitution, merge this together, solve for V, which is y over 2, plug it in here, and I get the following: 1 minus y squared over 4. And since V changes from 0 to 1, plug in 0, you get 1, plug in 1, you get 0. So x changes from 0 to 1. Or if you want to trace it back, you could see it differently, but let's just move on. Now, this right here is a parabola, but it's written the other way around. So it's not a parabola that opens up or down. It's going to open right or left. To reduce the talk and show you more, here's the graph. It's a parabola that opens to the left because of the minus, and it's wide because the leading coefficient is slowing you down, which is negative 1/4. And if you do the math, you could see the vertex is at 1, going to the right, shifted up 1 unit, and the y-intercepts will be 2 and negative 2. Now, we don't need all this, but this is like a reference that I'm telling you it's a parabola that opens left. And this is part of the parabola right here. Okay? So we just need this portion because of our limits. X changes from 0 to 1. From 1 to 0 to be careful. If you take your time, I'll show you. If Let's see right here. If v is 0, I end up with 1 minus 0, which is 1. So that's my start. I end up at x equals 1. If v goes all the way to 1, 1 minus 1 will be 0. So I'm going from 1 back to 0 as x coordinates or x values, from 1 to 0. All right. So that's kind of might be misleading to say from 0 to 1. It's actually starting at 1, going backwards to 0. As you could see the arrows right here. All right. So we're done with this one. Let's move on to S3. Same style, same idea, same concept. It ends up as a parabola that opens to the right and shifted down or left, in other words, 1. And that's how it looks like. And you could see more detail if you want to see it. And it's a parabola that looks like this, but we are limited with x from -1 to 0 as the conditions given. Just plug this in on the x value and you will see how the x value changes from -1 to 0, or differently from 0 to -1. Finally, S4. S4 is going down, and that shows that u is 0 and v changes from 1 to 0. Do the math. We have y equals 0. Plug it in here. I get x equals minus v squared. And y, the second part, is 2uv, but u is 0, so y is 0. All right. So that's for the y part. That's for the x part. X equals minus v squared and y equals 0. As v changes from 1 to 0, x will change from -1 to 0. And that will cover the last part. And here's the whole graph. S1, S2, S3 image, and S4 image. The whole thing changes, and it's a one-to-one function. As you could investigate more, that it's one-to-one. You could transform this to this and work from there. You might say, like, what's the point of that? And it's like time consuming to change. Well, sometimes you have to. You can't integrate straightforward sometimes without transferring. We learned in a lot of different sections, polar, transformation, cylindrical, spherical. All these becomes handy when you have the integral that you are dealing with, hard to integrate straightforward with a regular substitution as a u substitution. So we have sometimes to use different ways of substituting besides calling it polar or cylindrical or spherical. I have a good example that shows you why we do this in just a few minutes. Now let's see how change of variables affects a double integral. We start with a small rectangle S in the UV plane, whose lower left corner is the point u sub 0 v sub 0, and whose dimensions are delta u and delta v. So to make it simple, we just start with rectangular, and we're going to transform the whole thing here to this right here. So if looking at S right here, we start with the lower left corner, which is going to be imaged to the lower left corner, if you want to call it that way, as it's described. So we're going to go from u sub 0, v sub 0, to x sub 0, y sub 0. The image of S is a region R. The image of S is a region R in the xy plane, one of whose boundaries points is x sub 0, y sub 0, which is the image of u sub 0 and v sub 0, as I mentioned. So this point is coming from this point. The vector r uv pointing to this right here in vector language or calculus is actually the two components g of uv and I plus h of uv j is the position vector of the image of the point uv. Now, the equation of the lower side of S is v equals v sub 0. So this right here, when you have v equals v sub 0, when v is fixed, that will be the lower side of S, whose image curve is given by the vector function ru v sub 0. That's this right here. So this will be imaged right here. The tangent vector at x sub 0, y sub 0 to this image curve is. That's the first derivative with respect to u, since v is fixed in one direction, okay? When v is fixed, this is the tangent vector going this way to this kind of like curvy side. Similarly, the tangent vector on the other side right here, when you fix u and make it u equals u sub 0, when u is fixed, you are here, that's u is fixed, that's going to be imaged right here. And also we're going to take the tangent vector when u is fixed. Now, I know this is kind of lengthy notes, but the point is the final part of it and the use of it. So let's just stay with me for like a minute or two, and I'll give you the final thought of this whole idea. Now, we can approximate the image R by the parallelogram determined by the secant vectors. A while ago we studied dot product, cross product, but there is a lot of benefits of knowing dot product, cross product. The cross product magnitude gives you the area of the parallelogram. We learned that a few sections ago, but here we go. So now we have, let's add the image to see what I'm doing right here. R u sub 0 plus delta u v sub 0 minus R u sub 0 v sub 0 will be delta u ru. That's B right here. And this right here, let me see if I could see v sub 0 is the fixed. Yes. In this case right here, v sub 0 is fixed. That's A. So that's A and that's B. This means that we can approximate R by a parallelogram determined by the vectors delta u ru and delta v rv. And now we come to the parallelogram formed by the tangent vectors. So dv rv, that's dv rv, refers to B, because here I did not write B on A, just to keep you stay focused with me. This part right here, this part, the V part, sorry, the second part right here is the B. So the delta u ru when V is fixed, as you can see V did not change, will be the other part, which is A. Therefore, we can approximate the area of the shaded region as a parallelogram, which is part of the tangent plane, doing the cross product and taking the magnitude. By doing that, we could simplify this to the following. Let's take it to another page. I don't want to make it too small right here and make it fit. Here's another page. So this is a cross product. As I said, this is kind of like lengthy notes, but it's important to see where we're going and what's the benefit of all these statements and notes. So, computing the cross product, that's how we do the cross product. We have RU and RV, which was mentioned a few minutes ago. We just display them. And we take RU, which is delta x, delta u, delta y, delta u, 0 because there's no z component. Same thing right here. We do the cross product. The determinant that arises in this calculation is called the Jacobian. Okay, so the Jacobian is part of the transformation that happens in different topics like the polar form, the cylindrical form, the spherical form, and so on. But this one is in general. It doesn't have to be called polar form. The Jacobian of the transformation of t given by x equals g of uv and y equals h of uv is the following. That's the cross product that we have it, the determinant, of dxu. Now right here, if you notice, you might say like, why did you write it as dx dv here and dy du instead of the other way around? It doesn't matter, because once you multiply and you go back and multiply, these two will be multiplied either way, just to let you know. So you end up with the following. Here's the main part. The double integral of some region R, the dA or delta A, f of xy will be transformed to another region with the units u and v. We are going to change x to x u and v. We're going to change y to y u and v. And dA is not just du dv. This part shows up. In polar form, we did not go from dx dy to dr d theta only. R was part of the game. dA changed to dA, which is dx dy, in polar form changed to rdr d theta. Three pieces, r, dr, d theta. So r is part of the game that the Jacobian is talking about. I'll show you in just a minute what do I mean. So here's what you have to be careful also with. The inside part is the Jacobian. And when you apply the magnitude, I need the area of the parallelogram. So if the Jacobian is negative, I need it to be positive, because the Jacobian comes from finding the area of the parallelograms, which has to be positive. So keep this in mind. The first one right here is the determinant. This right here in green is the magnitude, which is not fully clear in textbooks, but I'm just saying this is determinant. Those vertical lines gives you the determinant. Once you find them, because we are looking for area of parallelogram, you want to make sure that you are taking the magnitude. Okay, so this is my dA in green, got replaced with three pieces in general. This is the main part. That's what you want, and it came from the figures or the graphs that we had earlier. So the Jacobian in polar form, we didn't have to do this, but it's a bonus. Let's take care of it, and I'll go quick. In polar form, we don't speak Jacobian. We just do it. But I want to speak now in terms of the Jacobian, what's happening. Take a look. We transform x and y to r cosine theta and r sine theta. We do this. We know this. This is the determinant. dx dr, dy dr, dx d theta, dy d theta. You take your time and you're going to end up with this. Let's just do the first one. dx dr with respect to r. I want to differentiate this. This is a constant in my way. So the derivative of r cosine theta with respect to r will give me cosine theta, which is right there. Then you know how to finish it. Multiply, go back and subtract the product of these two. And when you take the determinant, See, this right here is not part of the game. Those are the magnitude. I need the magnitude, which is not a big deal here because it's going to be r, and we don't know like if we're going to see a minus sign. But just to be on the safe side, the determinant is multiply this by this and go back and subtract the product of this diagonal. I added those vertical lines to be on the safe side for the magnitude. Alright, so it ends up r, and if you use a formula, I'll take you back. Let me show you. So this right here with the magnitude in polar form is r, and this is the r d theta. So as you can see, the Jacobian tells you what's missing when you transform from xy to a different form, which is r theta and beyond. Something shows up besides r and theta in polar form, and that is part of the Jacobian concept. Okay, let's move on. Evaluate the integral. Now you might say, as I said earlier, why do we need change of forms? It's too much work. Do we need it? And so on. Well, look at this one here. Evaluate the integral e to the power x plus y over x minus y dA, where r is the trapezoidal region with vertices 1, 0, 2, 0, 0, negative 2, and 0, negative 1. How are you going to do this? That's not a regular substitution, and that's not cylindrical polar form. We're going from point to point to point to point, and it's a trapezoid. So I think it does suggest we make a change of variables suggested by the form of this function. I mean, look at it. Take a look after this statement if it makes sense to you. What do you think? You plug in x plus y, or you change x plus y to you, not me, and x minus y to v. It kind of says it, what to change or what to substitute. I know with more experience and practice, you'll kind of like get the idea. But once you do this, you need to follow the rules and use the Jacobian. And if it's kind of hard, as you notice in the book and homework problems, they tell you what to substitute for u and what to substitute for v. If they don't, this is a great example to tell you how to think about change of variables. Okay, let's move on. Doing some algebra, I could solve for x, I could solve for y. The Jacobian is dxy, duv, dx du, dx dv, dy du, dy dv. Let's find dx du. Dx du will be just half, which is right there. So doing the whole thing right here, determinant, the determinant is negative half. I'm coloring this because I want you to pay attention to it. Half is not the determinant. It's negative half. But the Jacobian is part of the concept of finding the parallelogram area when you transform from region R to region S. So we need the magnitude. So just keep in mind that negative half is not going to stay negative half inside the integration. Now, to find the region S in the UV plane, this is my XY plane, and that's the region R speaking X and Y, and that's the region R speaking X and Y. Taking your time and plugging the points 1, 0, or marking them 2, 0, 0, negative 2, 0, negative 2, 0, negative 1, connecting them, and this is the trapezoid that they mentioned. Now, the region S will be transformed to these lines. And this is the transformation that is taking place, and this is the image. It's kind of time consuming to keep speaking back and forth and plug in the numbers and show you, but I'll show it to you either way, and I'll go a little bit fast so you could slow down and look at the notes if you want it. But that's the image. Let me show you how everything is transformed, but I don't want to slow down. As I say, like, I want to save you some time from just listening to me and speaking too many pieces back and forth. It's like a puzzle. If you take your time, you're gonna end up having the right image. I know it's time consuming, but it's part of what we have. So looking at S1, that's the first part right here. When x changes from 1 to 2. Now you don't have to call this one S1, you could start here, but this is what the image says. To start from here, x changes from 1 to 2, y is 0 because we are on the x-axis. Keep this in mind and just keep it for all the 4 sides. Well, u is x plus y and y is 0. Plug in 0 here, plug in 0 here, so u is x and v is x, as you can see right there. Well, that says also that u equals v. So on the uv plane, when you say like y equals x, that's like a 45-degree slope of 1, y-intercept 0. That's this line right here. If you connect it, it's u equals v, or v equals u, either way you want to call it. It's a 45-degree. And you need to know where it starts, where it ends. So it's not going to go all the way. With the limitations that we have, we end up with from 1, 1 to 2, 2. X changes from 1 to 2. So u will change from 1 to 2. And v will change from 1 to 2. And that is right there. Okay, one more time. If I keep talking this way, I might slow you down or confuse you, but instead of skipping that, I have it for you, as you can see. Here's S2. That's coming from this side. Here's S3. And here's S4. You could pause the video and look at the notes, but I don't think it's practical for me to read every single number right here and show you what every side is and how I got them. So I wrote them down for you. You could pause the video by hitting the space bar, and hitting the space bar again will play it again. So now you have them. Let's go back to the problem. So we are going from this to this. That tells me my limits on the new integrals. And one more time, this is my main problem, described right here. Kind of hard to integrate with the concept of u and v substitution using the Jacobian correctly. Notice that here I wrote half. I did not write negative half that I mentioned earlier. This is the magnitude. That's not the determinant. What's inside is the determinant. You do it on the side, come back right here. If it's negative, you make it positive. du dv, u goes from negative v to v, from negative v to v. So we're going like type 2 region, negative v to v, and 1 to 2 for the v part. This is the v part from 1 to 2, and that's why it's called type 2. So if you go with the arrow this way, that's called type 2. If you go with the arrow this way, that's called type 1. And after that, it's just like regular steps, and that should do it. I tried to make it less than 30 minutes, but it's a little bit harder because it's too many pieces inside. But Hopefully you got the idea of what is a Jacobian and how to take care of it. And this is a great example to show you, highlighting the main pieces. Why do you need it? Magnitude, not only determinant. New limits. Time consuming, I know, but it's worth it, because without that, it's almost impossible to integrate. Thank you for watching, and I'll see you next time. Thank you for watching. Don't forget to hit the like button, subscribe to see some more, and I'll see you in the next one.